All right, so this question here is using like the kinematics of motion in relation to maths methods concepts in like a complex familiar slash potentially unfamiliar, but I would probably say more leaning towards the complex familiar side of exam question. It is taken from a past external, so it is really good practice. So the first thing we need to look at is what we're initially given. So we're given the general information of a particle moving in a straight line with velocity given in meters per second, and given by this function here, where velocity is given with respect to time in seconds. And we're also given that the initial position of the particle, so when t equals 0, is at plus 6 meters, so positive 6 meters from the origin. So, part A, use calculus methods to determine an equation for the position of the particle from the origin at any time t. Okay, so essentially what that means is we need to go from velocity to position. And to do that, we integrate. So to get to position, or xt, we are integrating the velocity function. So this becomes the integral of 20 sine 2t all over 6 minus 5 cos 2t. Now this might look really confusing and impossible to integrate, but one key thing I want you to look at as a student looking at this is I want you to look at what you have on the denominator and what you have on the numerator and have a look at what you could potentially do. So looking here, we'll have something what we call the composite function rule. And essentially what that is it just means is when you have a function on the denominator, like we have here, if the derivative of that function is on the numerator, we can simplify that down to a natural log. So let's have a look. Let's say let u equal 6 minus 5 cos 2t. Then let's derive that. So 6 goes away, cos goes to go from sine to cos and cos to negative sine. So it becomes positive 5 sine 2t, and then obviously we have to chain on the derivative of what was in the brackets of the sine, so that's 2, so it becomes 10 sine 2t. So that's the derivative. And if we have a look up top here, we have something very close to that. So what I'll do is I'll bring this down here. We say, okay, if we want the derivative of what's of u, which is 6 minus 5 cos 2t, to be on the numerator, then we need 10 sine 2t. And so what I can do is if I take out a common factor, or if I just take out a factor of 2, look at that, we now have 10 sine 2t on the numerator, and then still 6 minus 5 cos 2t on the denominator. So, because we have the derivative on top and the original function down bottom, we can say, okay, we can use the composite function rule and say this is equal to 2 ln of 6 minus 5 cos 2t plus c. So this is the natural log of this whole function in here. That's what that means essentially. Okay, so that's the big first step essentially. And then the last bit is we need to get rid of this plus c to actually give us a proper function for the displacement or the position. And so we need to use this bit of information that we're given here, where the initial position is positive 6 meters from the origin. So what that means is, okay, when t equals, so this is xt, when t equals 0, x equals 6. And let's substitute that in. 6 equals 2 ln 6 minus 5 cos of 0, because 2 times 0 is just 0, all plus c. Okay, so we have 6 equals 2 ln, and cos of 0 is 1, so that's 6 minus 5, and that is just 1, plus c. Now, we know that log whatever base, any logarithm of 1 is 0. So we can say, okay, c equals 6. So this 2 ln 1 just equals 0. This is one of your log laws where ln 1 or log of anything 1 equals 0. Whatever the base is, it doesn't matter. Log of 1 is always going to be 0. So from there, we solve out. We've got c. So therefore, xt, or our position function, is given by 2 ln 6 minus 5 cos 2t plus 6. There you go. That's your answer to part A. Okay, now we're looking at part B. Determine the position of the particle relative to the origin when it first reaches maximum velocity. Okay, so from this point, what we do is, this is a tech active question. So what we can say here is we can go, okay, let's refer back to our graphing calculator or our graphics calculator. And we can go, okay, it's looking for the position of the particle relative to the origin when it first reaches the maximum velocity. And so what we can do is we can graph the function for velocity using our graphics calculator. You should just be able to go to the graph feature and type in 20 sine 2t, or in this case, you'd have to use x instead of t. Just otherwise, you'll confuse the calculator. And then all over 6 minus 5 cos 2t, or 2x in this case. Press that in and graph that. Naturally, the first time it reaches a maximum is going to be after t equals 0, as given to you in the question here. Time is greater than or equal to 0. And so if we just use the analyze graph feature, analyze for a maximum, you can see, oh, okay, there is a maximum. There is a maximum here where, so our first max velocity at, is it t equals, if I check the calculator, 0.293 seconds. And that's using our graphics calculator. Okay. So from there, all we have to do is find the position relative to the origin at this point. So that becomes as simple as substituting in t equals 0.293. Substitute that back into our original equation and show all our working to ensure we get the marks. 6 minus 5 cos 2 times 0.293 plus 6. Once again, because this is a tech active question, we can just refer back to our graphics calculator. Okay, let's plug all that in. 2 times ln 6 minus 5 cos 2 times 0.293 all plus 6. And that your calculator should spit out an answer that looks roughly like 7.21 meters. So 7.21 meters in a positive direction away from the origin.